So you can write the statement that scattering of alpha particle from a nucleus. So in scattering experiment, as alpha particle comes from infinity in close proximity of scattering nucleus, the Coulombic repulsion between the two increases. Okay, this would happen. So let us assume that during scattering experiment, what happens is alpha particle is coming from infinity in close boundary to this scattering nucleus, and as a result, because of the positive charge, they will get repelled. Okay, so when the nucleus and alpha particles are just touching each other, at that time we can say repulsion is maximum. Okay, when this Coulombic repulsion is maximum, it is maximum only when alpha particle and nucleus just touching. Don't assume that they are touching each other. Okay, they are very close. Just touching means very close proximity. Very close proximity. When they are very close to each other, then you can say that this Coulombic repulsion is maximum. Okay. Now, if the kinetic energy of alpha particle is larger than Coulombic repulsion, then what happens? Then this alpha particle can easily come out of that. Let's say this is the barrier. Let's say this is the alpha particle. If this alpha particle is moving with certain kinetic energy, and this kinetic energy, if it is less energy as compared to this repulsive energy, then this alpha particle can never come out of this potential barrier. Ideally, what quantum mechanics is telling is that this alpha particle penetrates through this barrier and comes to this side. That doesn't mean that it is jumping from this potential barrier like this, because it requires lots of energy and it is not getting any energy from anything. So then how it is possible to come to this side? Only possible way is, two possibilities are there. Either you gain energy, come out, or you leak through it. So since energy is not given by any other extra source, that means this alpha particle is slowly penetrating into this potential barrier and coming to this side. But this is classical mechanics doesn't approve this one. Okay, only quantum mechanics says that. So you have to overcome this Coulombic repulsion. So if this alpha particle is not having that much of energy, and how this kinetic energy will increase, because mass remains same of this alpha particle. Only if the alpha particle is coming with a greater speed, velocity, then only kinetic energy will be maximum. So if this kinetic energy of this alpha particle is greater than this potential barrier, this potential barrier energy, that means this Coulombic energy, then only the alpha particle can leak through the barrier. That is called tunneling. Okay. So in that case, how this graph will look like? Like this. Okay. So if you see this figure, then what does this figure tells you is that from B to A, this is the R. R means the range. Okay. And this is the potential. Okay. So from A to B, that means what is happening? potential is increasing. As R is decreasing, potential is increasing. That means this is the electrostatic repulsion case of alpha particle as it approaches the nucleus. कहने का मतलब ये है कि मान लो ये आपका न्यूक्लियस का बाउंड्री है, ये अगर आपको इस बाउंड्री को क्रॉस करना है, यू हैव टू कम फ्रॉम अ वेरी फार डिस्टेंस विद ग्रेटर वेलोसिटी एंड टनल इनटू इट. But if you are coming at a very slow speed, or you are, let's say, very close proximity of this nucleus boundary, then you cannot tunnel into it because Coulombic repulsion is maximum. That is the case of this one. That means the R here is very less. So here R is close to, or you can say, this alpha particle at B point, alpha particle and nucleus boundary is very, very close. As a result, here you have electrostatic repulsion. Okay. Now, gradually, when it comes down from B to C, the sharp fall from B to C is a region within the nucleus. That means it implies attraction of alpha particle by the nucleons present in the nucleus. Okay. So gradually, when you come away from this B, or you come towards A, that means this direction, that means with increasing R, gradually your electrostatic repulsion is decreasing, and you have sufficient energy to overcome, or you can say cross, not overcome, right? Overcome is not the right word. You can say cross across this barrier, penetrates through this barrier. You can say that the alpha particle now penetrates through this potential barrier only when kinetic energy of alpha particle is greater than the potential barrier energy. Understood? So from calculation, it is found that this energy is roughly about 25 mega electron volts for higher elements, for higher Z elements, atomic number elements. This is 25 mega electron volts. But experimentally, it has been seen surprisingly that few radioactive elements whose energy is much low than, this is what experimentally observed, that in case of few radioactive elements, the energy range is close to 4 to 5 mega electron volts, and this particular energy of alpha particle is able to cross this potential barrier. Okay, so how it is possible? Either by jumping or by tunneling. Jumping is not possible. Okay, two things can happen, either by jumping or by tunneling. Jumping is not possible. Why? Because alpha particle is itself having very less energy as compared to this 25 mega electron volts, and you are not giving any extra energy from outside. Am I audible to all?
Yes, sir.
So tunneling is the only way to have this. So that process is called your quantum mechanical tunneling. Did you understand now? Yes or no?
Yes, sir.
So this probability, there is a small probability that such particles from the interior can be found outside the nucleus. This is the outside nucleus. This one is outside nucleus. This is inside. So there is a very small probability that alpha particle can be present or found outside the nucleus, and it is only possible through quantum mechanical tunneling. So that is why this is called tunneling or quantum mechanical tunneling, or you can say that quantum mechanically. What you write the statement? Quantum mechanically, there is a small probability that alpha particle leaks or penetrates through the potential barrier. This process is called quantum mechanical tunneling.